Have you ever really stopped to think about how incredible it is that we can see inside the human brain? I mean, without a single cut. Or, and this is the really wild part, how scientists can literally watch your brain light up while you're thinking? It sounds like magic, but today we're going to pull back the curtain on the technology that does it all, MRI and its cousin, fMRI.
Seriously, how can you take a picture of a thought? It sounds like something straight out of science fiction. But here's the thing. To figure out how it works, we don't start with the brain at all. Nope, we start with something way, way simpler. The one thing that makes up most of you.
Okay, let's dive into this. It all kicks off with the very first letter in MRI, the M, which stands for magnetism. And the key here isn't some rare, complicated element. It's actually something that's already inside every single one of us, right now. See, your body is about 60% water. And water, as we know, is H2O. It's that H, the hydrogen atom, that's the real hero of this story. Or, to be more specific, the proton at the heart of that hydrogen atom. An MRI machine, at its core, it's just a really, really fancy proton detector, building a map of all that water in your body.
So every single one of these little protons has this weird quantum property called spin. Now, don't worry about the physics too much. The easiest way to picture it is that each proton acts like a tiny microscopic compass needle. It's got its own little north and south pole just spinning away.
Okay, so right now, all those tiny compasses inside you are pointing in totally random directions. They're all over the place, canceling each other out, so there's no overall signal. But the second you slide into an MRI machine with its ridiculously powerful magnet, wham! They all snap to attention. Well, most of them. A slight majority all line up in the same direction, and for the first time, they create one single detectable magnetic signal. And that's what the machine can finally listen to. All right, so we've got all our little compasses lined up, pointing in the same direction. Great. But how do we actually get a signal from them? They're just sitting there. Well, that brings us to the R in MRI, resonance. We basically have to get them to talk to us.
And here's how we do it. The scanner sends in a quick pulse of radio waves. Think of it like a little energy ping. This pulse is tuned to a very specific frequency that has just enough energy to knock those aligned protons sideways. Then the machine goes completely silent and it just listens. As those protons start to wobble back into alignment, they give off their own tiny radio signal. It's like an echo, and that's the signal the scanner is built to pick up.
And this is the part I think is so cool. The frequency of that little echo, for a standard MRI scanner, it's about 127 megahertz. Now, if you've ever looked at an old FM radio dial, you'd find 127 right in the middle of it. So what an MRI machine is really doing is, it's a super sensitive radio receiver tuned to a station being broadcast by the atoms inside your own body. How amazing is that?
Okay, so we're listening to this radio broadcast from our body's protons. That tells us, hey, there's tissue here. But right now, it's just one big blended signal from your entire head or whatever part is being scanned. It's a mush. So how on earth do we turn that mush into a detailed picture? Well, that's where the I comes in, imaging. This really is the million-dollar question, right? If all the protons are singing at the same frequency, how can you possibly tell where any given signal is coming from? How do you know if it's from your nose or the back of your head? The solution to this puzzle is honestly just pure genius. They use something called a gradient field. Basically, they turn on a set of smaller magnets that deliberately make the main magnetic field uneven. So instead of being the same strength everywhere, now the field is a little bit stronger at, say, the top of your head, and it gets progressively weaker as you go down towards your chin. Here's a great way to think about it. Imagine you put 2 glasses of water in the scanner. Without that gradient, they're in the same magnetic field, so they both sing back at the exact same frequency. You just hear one note. But turn on the gradient, and now the glass on the right is in a stronger field. The protons there spin faster, so it sings a higher-pitched note. Suddenly, you can tell them apart. By listening to the pitch of the radio signal, the computer can figure out exactly where it's coming from and build a pixel-by-pixel map. So clever! And just like that, we have an incredible, high-resolution map of the brain's structure, a perfect anatomical picture. But what if we want to see it in action? What if we want to see a movie instead of just a photo? Well, that's where the little f comes in, turning MRI into fMRI for functional. Now, here's a really important thing to understand. fMRI isn't actually seeing your neurons firing. That's an electrical signal, and it happens way too fast for the scanner to catch. Instead, it's watching a side effect. It's tracking the rush of blood that flows into an area right after the neurons there have fired. The technique is called the BOLD signal. That stands for blood, oxygen, level, dependent. And it all hinges on this really fascinating quirk of your own blood. It actually changes its magnetic properties depending on whether or not it's carrying oxygen. Okay, get this. When blood has dropped off its oxygen, so it's oxygen poor, it's actually slightly magnetic. It messes with the local magnetic field and makes the MRI signal weaker. But when that same blood is fully loaded with oxygen, it's not magnetic at all. It's basically invisible to the magnet, just like the surrounding tissue. This one little difference is everything. And that difference creates this incredible chain of events. So a bunch of neurons in your brain fire, they get active, they use up oxygen. Immediately, your brain goes, whoa, need more fuel over here, and it sends a massive rush of fresh, oxygen-rich blood to that spot. It actually overcompensates, sending way more than needed. And this flood of magnetically invisible blood pushes away all the magnetically disruptive old blood. The local magnetic field gets smoother, the signal interference goes away, and the MRI signal from that one tiny spot gets stronger and brighter. And that bright spot you see on an fMRI scan, that is the picture of a thought. So there it is. We went from a tiny wobbling atom and a drop of water to lining them all up with a giant magnet, to making them sing with a radio pulse, to figuring out where they are by changing the pitch of their song, and finally to watching how a rush of blood changes that song to reveal a thought. It's just an absolutely incredible journey from the most basic physics right into a window looking at the human mind. And this technology is getting better every single day. We're getting sharper pictures, faster scans, a clearer and clearer window into our own minds at work. It really makes you wonder, doesn't it? Now that we have this incredible tool to look inside ourselves, what are we going to discover next?